Hello everyone, we are back now to talk about generative models. Generative models, it's a model that it's used to generate realistic but fake images about anything. In this example here, generative model was used to generate faces. But in our example, we are going to try to generate anime faces because it is easier and will require less computer power to train the model. Generate something like a face will take a very long time training our model and would require a lot of computer power. Before we dig deeper in our lesson, I would like to call out that I'm basically using our example that is available on Jovian, and I will suggest you guys to check it out, this series about deep learning with PyTorch from zero to GANs, which is very nice series which contain videos on the YouTube and everything. So he did a very good job here creating a very descriptive notebook, and I will leverage from some stuff here because it's just here already. I did some tweaks for our example and for better explanation. So for example, this image I have replaced with this one and has removed some other stuff that is not really required. So yeah, I was planning to create a new one, but since it has this one available already, so let's just use it. And I hope, and then I take the opportunity to tell you guys about this very nice work done by Cash something. And the whole platform is very cool as well for when you are building your model, which you can record and track the progress of your model as you are changing. Okay, so deep in our example, quick one. So we are going trying to generate images, right? And that image we expect that follows a pattern. So if, for example, if we are talking about faces, we need to be able to make our generated images look like a human face, right? And this is an example that NVIDIA have created. So NVIDIA is the company that like responsible for create GPUs. So they have a lot of computer power to put and make all that available. So in our example here, let's just quickly talk what generative image model, right? So what we are trying to build exactly is generate images from a random input. This random input will just basically control, it would work as a seed to control what we are generating. And I think worth going back from to our previous example, where we also generated new images, right? So which was numbers in our case. And how we did that, just a quick recap, we were generating latent space based on the standard deviation and the mean of our existing latent space. So before we had to create a latent space from another model, right? Was the encoder, and you were transforming this latent space, and our decoder was creating the image. And now we are focusing on this generator, so we don't want to have this first part and create a latent space to only from this latent space transform a latent space, so we'll be able to generate it. We really want to generate random image and be and for that we are gonna focus we are gonna be creating a generated model, and it's very interesting how we do that using GANs, right? And in order to do that, to have a very good generator, we need to create another model that we call Discriminator, and we work together to we're using these two models to train our generator. So as the previous lesson, we are going to have two models. However, this model will be used only on the training phase. Okay, that will be used only just to help train our generator. And how we are going to see in the code will be easier to understand that, but basically this discriminator will basically tell if the image generated by our generator it is a fake or a real image. So and the training will be basically trying to create a generate a model that is able to fool the discriminator, and that's how we see how good it's our generated model. It's how good it is able to fool our discriminator. Let's try to see if the code helps us to understand better this. And so as I said, you're going to be using an image, okay, and we are going to be downloaded from this data set from Cargo, and we have here everything that we need. We need to have the Cargo account with the API, so we already saw that in the previous lesson, so it should not be anything new here. Then we look our data, so we can see some example of the image here, and one important part, we are going to be using stats for normalize our images. So we are trying to avoid the saturation, right, as we already talked. So it's important to our image not be don't have high pixel values, and also not very low, so this big discrepancy would misleading our model. So we'll do this as a way to avoid that. And here it's where we are normalizing things, and because we are doing that, when you are displaying the image, showing the image, we need to denormalize, so put it back what was before. So I commented here. Here are example of the images that we have in our data set, and now we are going to be talking a little bit about discriminator network or model. Okay, so basically, as we already said, the discriminator takes on an image and tries to classify it as a real or a generated or fake image. Okay, that's the goal of this discriminator model. Let's see at the network architecture for it. So here we are not using a class to create our model, but just using a function from PyTorch. But we have seen that already. So we just create different layers, right? In our case here, convolutional, we have 3, 4, 5 convolutional layer that we already saw those. So something different that we are using is leaky Relu instead of Relu, and we are talking a little bit about what is leaky Relu activation. So it's basically the same Relu, but Relu would be only everything that below 0 will be 0. Here we give some extra let's say buffer to return some negative value. So very simple. And we are using Sigmoid as the output layer. We already saw Sigmoid, so very simple. It's basically that. So then we create a discriminator, we add to the GPU, and now it is the generator network. So nothing much different from what we have seen before. Again, just creating a model using sequence, and now we are doing as we saw on the autoencoder, we just go backward. So now we are giving latent space flattened, and then we just go trying to reproduce, increase the values of the matrix, right? So we start to 1 by 1, then 44, 88, 16, 32, 64. And in our discriminator, if you see, we start with 64 and going down, decreasing the value, while it is increasing the, let's say the, how can we call this, the dimension, the z dimension. And the dimension here starts very high, which is 138, and going down until the 3, what was the original. So is in the counter direction of the same way we saw on the autoencode. So the two models is going the opposite directions. Here we use tan as the output instead of sigmoid, but it's the same. So sigmoid goes -1 until 1, or tan go everything that it's below -1, you're gonna be -1. Everything that up bigger than 1 would be 1. So we have this tangent. So how to choose tan or Relu or sigmoid? It's only by experimenting. You have to experiment with the one would be it's better for your model. So it is pretty boring. Creating a model, it is pretty boring thing. So it's you have to keep experimenting and try and tracking the performance of your model. So in the case here, the creator of this model has tried all the possibility and changed the parameter number of neurons and everything, the learning rate, in order to try to achieve optimal result. So in here they tried tan, and that's the one behaved the best. So now we have our generator model, but we haven't trained it yet. So and then we try to use it here before training and see that generated image. It is basically nothing. It's a bunch of pixels with no real images. So then we talk a little bit about our discriminator training. So we're going to create a function for that, and as we saw, discriminator, it's a binary classification. I'm going to say if the image is true or false, right? And so we start our discriminator, and we see how what's the result for a given image, and then we put everything 1 because we are working with the real images. So everything it's true should be true. And then we just compare what is discriminator returning versus being true, and this use another loss function that is binary cross entropy. I think it's the first time that we saw this function, but there is many others, and depending on your problem, you're going to be picking different ones. So in our case here, it's a binary cross entropy. Then as before, we always get the mean of the predictions, and then we pass the fake images. So we pass fake image with everything with 0, and use the discriminator with fake images. Fake image we get from the generator. So we're using the generator here to first, I was skipping things, sorry. We need to generate fake images, and in order to generate fake images, we need to create some random data, okay? And use the random as before we saw already, and then pass this random latent to the generator, and the generator will be creating fake images. And then we know that everything is fake images, so you create a tensor with zeros, right? And then discriminator try to see if it is true, if it is fake or real, and you get the result. And then we check again how good it was able to say that it was fake. And then we sum those two losses, and we update the weights, and we return it. So you see how the interesting part of when you build a model, it is come up with a good a good way to measure the losses, right? And here we have seen that has a very interesting way to do that, and it is basically using the other our generator and with the real image all together, and in the end we sum things, and that the result of this would help us to see if our model it's improving or not. Okay, let's look at our generator training process. So it's pretty simple. So we start generating an image based on a random latent, and then you get the fake image. Then we pass to our discriminator. Remember when we said that the goal of our generator it is to fool our discriminator. So we create the image, fake image, pass to discriminator, and we check how good was the discriminator to identify that our image is fake. So we just see the loss, and yeah, it is based on that. So we use our discriminator to check how good we are to generate fake image. So as we are better in fooling our discriminator, means that our generator is getting better and better. And it's pretty simple, but it's pretty let's say tricky creative way of calculate our loss. So then we create a function to save our images that we are generating, and this way you can see the progress of our model. And let's say, for example, if you try to see an image now that's generated before training, very bad, nothing really represented here, it's just random pixels. Then let's look at the training loop, right? So everything together. As I said, so that's the basically architecture. So we try to generate some image example, and we train our discriminator to learn how to check to identify fake images, and then we use the same discriminator that we are learning to identify fake image to see how good it is the image that is being generated by our generator model. I think the code will be easier to see. So we start training our discriminator with real images, and then we train our generator with that we already saw that using discriminator inside, and we just keep tracking this process, this loop. It's train discriminator first and use the discriminator to and we would see how good is the generator to create the model, and we just keep track of the losses and the scores on the appearance of the models, and we save the images to see what the image that was generated, how good the image are, as we iterate on our epochs. So we have here the learning rate will be 0.02, and we're going to go through 25 epochs. To get a very good result, you'll have to go over more epochs, but that will take longer and longer, very long. So we are using 25, and we're going to see what we can get with 25 epochs. So then we start our training, and you can see that we are saving every image, and here we can see the result. So we can see that the first try we generate pretty bad images with very bad colors. Then after 5 epochs we get a bit better, but still not perfect, right? So the colors is not very good. The face is not really clear. You see, look, this face here is very strange. But then after 5 more epochs, we get way better color, and the faces is more realistic, more close. It's closer to the real ones. And after 20 epochs, it will improve a bit more, right? It's pretty good. Some of the examples, we still have some kind of awkward result. For example, this one, but it is pretty good. And then after 25, we have really pretty good result, right? So very much realistic to what we had the real example. And so with that, we can basically see that we are able to generate random. So none of those here is the same as it was the original one. It's everything different. Something will be different at least. Looking at the loss or the behavior of our model during the training, it's pretty hard to see if our model is improving over time, because it's very random results, and that's why we look at the image, the result of the image, to see if our model is really improving or not. So we cannot really rely on on, let's say, the statistic of the model, the losses and the occurrence. So it's pretty random due to the complex of the calculations, and because it's random images. But that's it. So that I use this example to kind of show some interesting way of build models and to calculate loss and occurrence and everything. I hope you guys have enjoyed this example, and thanks for your time.